In this video, we're going to talk about the equilibrium constant. Now, the equilibrium constant is a value that is determined experimentally, and it applies to a reaction system at a specific temperature and pressure. So the reaction equilibrium requires you to know the temperature, so it's usually listed. You'll never use the temperature for a specific calculation, but temperature is kind of what affects the equilibrium constant value. The equilibrium constant is referred to as Kc. Sometimes it's KEQ. If you're looking online, you'll see other things that are the subscript, but K means the constant, and that subscript, in this case C, means equilibrium constant. So the Kc depends on the concentration of the reactants and products at equilibrium, as well as the coefficients of those chemicals. We only calculate the equilibrium constant for things that have mole per liter or millimole per liter concentration in Chem 30. It's possible to calculate an equilibrium constant using pressure for a constant volume, but we don't do that in this course. We're only going to use things that use mole per liter or millimole per liter. And so that includes gases, aqueous solutions, or less common solutions like things dissolved in alcohol. So it's possible to actually dissolve a bunch of things in alcohol and it makes a solution. And when we would write it, so let's say that we were to dissolve sugar in water, it'd be written like this. That's an aqueous solution. But if we instead dissolve that sugar in alcohol, it would be AlC for alk. And so we could calculate a mole per liter concentration for either an aqueous solution, an alcohol solution, or for a gas. So Kc calculations are unaffected by solids and liquids. So those are considered constants when we talk about equilibrium systems, and so they do not get into the calculation. Now we're going to use this very bizarre reaction to show the pattern, but it's just a pattern. So here we've got chemical A, chemical B, C, and D, and their coefficients are written as the lowercase letter. So if that's our equilibrium system and those were all gases or aqueous or something with mole per liter, the Kc is calculated like this, where I calculate the concentration in mole per liter of a product raised to its coefficient times the molar concentration of another product raised to its coefficient divided by the concentration of a reactant to its coefficient times the concentration of the other reactant raised to its coefficient. And so that's what this means. We'll never actually properly use that equation. We're going to use that pattern to figure out other equilibrium constants. So you should know that the equilibrium constant value always is temperature dependent. It does not matter what concentration we start with of any of the chemicals, because the constant only applies to the equilibrium system. Once it gets to equilibrium, that's when the Kc can be obtained. So what we start with doesn't matter. It's going to get to a concentration that makes it that equilibrium constant. Catalysts don't affect the Kc. It just speeds up getting to the equilibrium constant. And it doesn't matter how long it takes to get to equilibrium, so we don't care about that. There are numerical, it is like the Kc, equilibrium constant is a numerical value. It's not that there couldn't be units, it's that we ignore them because the units are different depending on what you've got. So for instance, if we had this equation, I'd have mole per liter times mole per liter. If each of those coefficients was, each of these was like the coefficients were 1, it'd be mole per liter times mole per liter divided by mole per liter divided by mole per liter. Well, all the units would cancel out and there'd be no units. But if instead we got rid of that, now the units would be mole per liter. right? Because I have mole per liter in the numerator squared divided by mole per liter. And so because the units can vary depending on how many reactants and products there are, they just ignore the units. We just don't write any units for it. And there aren't a lot of things that we don't write units for in chemistry. This is one of them. Also, the equilibrium constant value. The bigger the number, the more positive the exponent, the bigger the number, the more it favors the products. Because it's essentially saying that we've got a bigger amount of products than we have of the reactants. So as the Kc increases, I know that I am getting more of that product than reactant. If the Kc is smaller, it means we've got more reactant and less product being made. Okay, because the Kc essentially is got the concentration of products over the concentration of reactants is a way to think of it. It's a little oversimplified, but if we get a lot of products, we get a big Kc. If we have a little bit of, most of the stays as reactants, then the Kc is going to be a pretty small value. Okay, to calculate the Kc, we need the equilibrium concentration of things. So in this question, they're asking for the equilibrium constant for this reaction, and they're giving us the equilibrium concentrations here of the chemicals, right? And so if I've got the equilibrium concentration of both hydrogen and iodine, as well as hydrogen iodide, then my equation, because I have two hydrogen iodides, has Hi squared divided by the concentration of hydrogen and iodine. So I substitute those numbers in, and I come out with the equilibrium constant of 53. So equilibrium constant calculations always require the equilibrium value, and we can get that number from an ICE table. So for instance, if we wanted the equilibrium constant for this reaction, the reaction had hydrogen and iodine, so this was the Kc equals the concentration of hydrogen iodide squared over the concentration of hydrogen and iodine. And so it's going to be equal to, I'm going to use these numbers, my hydrogen iodide is 7.2 mole per liter squared over the concentration of hydrogen, which is 2.4 mole per liter, and 0.40 mole per liter. And when I put that into my calculator, I'm going to get 7.2 squared divided by 2. And I get a Kc of 54, which is almost the same value as we had in this question here, right? Because it's the same reaction, if it was at the same temperature, the Kc value should be just the same. If I was looking at this reaction, in this case, my Kc is going to be equal to the concentration of C2H4Br2 divided by the concentration of ethene at equilibrium and bromine. So it would be equal to the equilibrium concentration of the product, so 1.50 mole per liter squared over the concentration of 2.50 mole per liter raised to the power of 1, because the coefficient is 1. In this case, all of them are. And then 1.00 mole per liter. And my equilibrium constant for this will be, oh, sorry, this is wrong. I apologize. This is not squared because the formula was 1 to 1 to 1. So the 1.50 should not be squared. So my equilibrium constant for this is going to be 0.60, and there are no units for it. Okay? So the equilibrium constant, you need to know that it's only really affected by temperature. We calculate the equilibrium constant using experimental values for the equilibrium, and that It's the concentration of the products raised to their equilibrium or to their coefficients divided by the reactants raised to their coefficients. We'll give you a chance to do some practice questions related to that.